I think it's getting recorded. Okay, hello everyone. Good morning, all of you. So we start with today's quote by one of the great personality, Oprah Winfrey. The great woman, entrepreneur, multimillionaire. But the main thing, if you see the autobiography of Oprah Winfrey, it's highly inspiring. She is a black girl and very, very poor girl from very slums, and she became one of the millionaire. But the way is not so easily laden, right? She has faced a lot of problems. A lot of who normally cannot get such types of problems. She faced so many problems. And she says, be thankful for what you have. You will end up having more. If you are thankful, you will be given more and more. If you concentrate on what you don't have, you will never ever have enough. Because nobody can have the world. Everybody will have something and will not have something. And if you see at what you have, you will be always happy and you will get more and more. But if you see what you don't have, okay, there is so much everybody which they don't have. So you will never have enough and you will never have satisfaction. Okay, and today is the birthday of Kushwant Singh, who is author, lawyer, diplomat, journalist, and politician. His experience in the 1947 partition of India inspired him to write Train to Pakistan in 1956, made into film in 1998, which became his most well-known novel. He was appointed journalist in the All India Radio in 1951 and then moved to the Department of Mass Communications of UNESCO at Paris in 1956. These last two careers encouraged him to pursue literary career. As a writer, he was best known for his trenchant secularism, humor, sarcasm, and an abiding love of poetry. And Kushwant Singh was awarded the Padma Bhushan in 1974. However, he returned the award in 1984 in protest against Operation Blue Star, in which Indian Army raided Amritsar. See, you can see his personality, understand his values. But again, in 2007, he was awarded the Padma Vibhushan, the second highest civilian award in India. Okay, that is about the great personality Kushwant Singh. And so if you see elliptic solvers we have started in the last class. So in the last class, whatever we have done is using recurrence relations with difference operators, we have developed the finite difference equations. So there we have seen a shortcut to get the finite difference equations to any order, right? Very fast you can get, whether it is forward, backward, or central difference, you can get it very fast. Only thing is we will get at first order accuracy only. That is the limitation for that. Then we came to elliptic solvers. We have seen what are the practical situations where you get the elliptic problems. Mainly whenever I have diffusion term, right, or Laplace's equation or the Poisson's equation, then it is an elliptic problem. And so if you take del square t in 2D, so we can discretize it either using 5-point formula or 9-point formula. 5-point formula gives in second order accuracy, 9-point formula gives fourth order accuracy. But we have seen what are the limitations of 9-point formula, because if you want to take apply the equation at the points near to the boundary, you cannot have the neighboring points, two neighboring points on all the sides. Okay, here also I told 5-point, 9-point, it is only for 2D. If you go for 3D, how many points you will get? How many points you will get for second order accuracy and fourth order accuracy? Anybody? See, somebody
7
has.
and 11.
Yeah. Yes.
7 and 11.
Yeah. 7 and
11.
11. Are you sure? 4 sides, 4 into 2 jar, 8 plus 1, 9. Now 6 sides will be there. 6 into 2, 12 plus 1. Am I clear?
Yes.
2 points on all sides, and point itself will be there. And here 5 point, 1 point on all sides, 1 point itself. So if it is 3D, I will have 7 points. If it is uh, say fourth order accuracy, I will have 13 points. Okay, then we have compared the direct and iterative methods. So we have seen that when I have direct method, it takes a lot of time, it takes a lot of space, and it is highly expensive. And the main limitation is round of error. And in iterative methods, those problems will not be there. So normally we prefer iterative methods in CFD. So we have seen various methods like point Jacobi iteration method. And in the point Jacobi iteration method, whenever you update a value, we use all the old values. And then point Gauss-Seidel iteration method. Gauss-Seidel, they came with a modified method or improved method telling that use the points as and when they are updated. So which reduces the number of iterations. And then point successive over relaxation. That is, if you want to make it faster to grow, because these are linear equations, you can always over relax it. That is, instead of adding that addition, I multiply it with some, it is like giving factor of safety or something, right? You multiply by more than one and you add it so that the convergence will be accelerated. But as I told, you cannot take any value, right? So don't give relaxation parameter 2 or 3 or like that. So then it will not converge. We will see a practical example we see from the code. Okay. Then the line Gauss-Seidel iteration method. Point Gauss-Seidel iteration method is like explicit method. There is only one unknown and all other unknown values. And line Gauss-Seidel, what we do is we solve, instead of solving point by point, we solve line by line. Okay, so that is called line Gauss-Seidel method. There will be 3 unknowns. So when you solve it, I am going to get a tridiagonal matrix. So this tridiagonal matrix, there is a okay. So this is called as actually TDMA, means tridiagonal matrix algorithm. So this is developed by a man called Thomas. So many times this is called as Thomas algorithm. So it is very, very popular, and CFD people love to use it. It's very, very efficient, highly efficient. Okay, what is that advantage of this? Suppose I have n by n point, n points are there, or I have a matrix n by n. Suppose if n equal to 1000, so how many elements will be there in that? So 1000 square. Okay, so 10 power 6 elements will be there. So I have to store so many elements. But we know that except these 3 lines, all are zeros. Okay, so how many elements will be there? Other than zeros? Anybody?
2998.
Okay, in terms of n,
3n minus 2.
yeah, 3n minus 2 values will be there, right? So if it is this, so 3000 minus 2, that is 2998 point values. So instead of 10 power 6 values, it takes only, the values are only this much. So the algorithm is written in such a way that storing only these values, the equations can be solved. Okay, so this actually uses like Gauss elimination only. So what it will do is using this point, this value, make this 0. Using this value, make this 0. Using this value, make this 0. So like that, these values are made into 0. So it will become like upper triangular matrix. So I need not have all these values. I need not operate on all the values, only on this particular value. And this is operated only on this particular value when you do the row operations. So that is the advantage of it. And then the back substitution. Same thing like Gauss elimination only, but the number of elements stored and the number of calculations are very, very few. It's highly efficient. So that's why people like to use it as a tridiagonal matrix whenever is possible, right? So here in line Gauss Seidel, we are going to have only 3 unknowns. So this can be used, Thomas algorithm can be used there. So that is the advantage of line Gauss Seidel iteration method. And again, line successive over relaxation. If you give relaxation here, you will get LSOR. And alternating direction implicit method. Okay, so here it is implicit also is there. Okay, alternating direction implicit ADI. Okay, so because this is implicit method, line successive relaxation also, or line Gauss Seidel also implicit method only, because there are more than one unknown. Okay, and so I told you the comparison of explicit and implicit methods. Explicit methods are easier to write the program, easier to understand, and the complexity, mathematical complexity will be less, right? But the number of iterations will be very high. Line Gauss Seidel, the time taken per iteration is very less in the explicit method or point Gauss Seidel. In line Gauss Seidel, in implicit method, the calculations per iteration will be more because I have to solve the equations, but the number of iterations will be very few. And as I told, when you go to parabolic and hyperbolic, there is one more advantage of implicit is that explicit methods are usually conditionally stable. They will be stable only if I satisfy some condition. But implicit methods, there is no restriction, there is no condition. They are unconditionally stable. So these are the comparisons between explicit and implicit methods. So ADI method also, so you can actually sweep, right? You can go line by line like this and then line by line like this. Or if you want to do the other way, you can do line by line like this and then line by line like this. So these two sweeps together, we call it as one iteration. Right? So that is the way we do it. These are the things we have discussed in the last class. Because these are all the things which we have seen. Okay. Now we will see one application. So there is a problem here, a rectangular plate. Okay. So a 2D plate, rectangular plate is there. And so here, so this is governed by if the temperature variation, if there is any there, it gets diffused. Okay, so the effect, if there is one high temperature at some point, so it affects the neighboring points and it gets distributed. So here, suppose I have Dirichlet conditions on all the 4 sides. Okay, so this is a particular problem where I have 0 degrees here, 0 degrees here, 0 degrees here, and 100 degrees here, like that. So if I have in that fashion, how the distribution will be? It will be like this. Sorry, it will be like this. The solution is this way. So you can solve, because del square t equal to 0, it is a linear equation, Laplace's equation. You can solve it analytically. So in the mathematics, normally people say how to solve them if you take a partial differential equation course. So they will tell you this is the way you can solve it. This is the analytical solution. If I draw the temperature distribution, I'm going to get this way. Okay, so this is to be solved numerically because I have del square t equal to 0. Using the 5-point formula, we can write the equation, and then I can solve it either point Gauss Seidel, PSOR, LGS, LSOR, ADI, or ADI-OR. So any method I can solve. And So here, using relaxation method, if I want, as I told you, what is the relaxation parameter I have to give, and what is the optimum value. So if you want to know, you find out what are the number of iterations you will get by changing the relaxation parameter. If I give 0.8, the number of iterations take like this, and 1, the number of iterations is this. 1.2, this is 1.4, the number of iterations are only 300. Otherwise, it is 900. Or if there is no relaxation, it takes 600 iterations. And if I take 1.8, the number of iterations will be very few. Okay, some 60 or 80 iterations or something like that. And again, if I increase the iteration relaxation parameter further, the number of iterations will increase. And not only increase, sometimes it will become unstable. So we will see that later. So relaxation parameter for LSOR, that is for PSOR, and this is for LSOR. And this is for ADA with relaxation. So the optimum relaxation factor will change with the method, whether it is point Gauss Seidel or line Gauss Seidel or ADA. Okay, and so the number of iterations that will take for point Gauss Seidel, line Gauss Seidel, and PSOR. So this you can see how many iterations it will take. Okay, this is error. So error gradually decrease, and it will be very less here when the number of iterations are some 580 or something. This is point Gauss Seidel. Line Gauss Seidel, the 300 iterations. And the ADA, sorry, this is PSOR, it will be only very few iterations. Okay, this is the way it will be. Okay, now actually I like to show. Okay, here I have written a code. This is solution of elliptic equations. Okay, submitted by Gupta. So here I have, it asks the choice of scheme. Okay, whether you want PSOR, PGS. Okay, available choices: 1 PGS, 2 PSOR, 3 LGS, LSOR, ADA, ADA-OR, like that. So it asks which scheme you want. So based on what number you give, it chooses that. So if I give 1, it will give in the printout that it is point Gauss Seidel scheme. If it is 2, it is point successive over relaxation scheme. Like that, it will indicate okay which scheme it is using. Then actual data is like this. Okay, so omega is the relaxation parameter. This also it asks the user. Okay, what is the value of relaxation parameter? That is omega. And epsilon, this is convergence check. 0.0001 I have given. Okay, up to so much of approximation, and n equal to 5000. Okay, if the sometimes it may not converge, it may go to infinite loop, so I have to put some restriction. So I have given 5000 iteration. Within that, if it converges, it comes out, no problem, it gives the result. Otherwise, it will come out telling that the program is wrong or there is no solution like that. Okay, so here length is equal to 1 meter and height is equal to 2 meter. In the problem, it is given feet. I have given it is meters. It doesn't matter, right? So 1 and 2. And so I have taken actually this also is given in the problem that what is the dx and dy you have to take. So dx is 0.05 and dy is 0.05. So how many grid points I will get?
18.
Dx is 0.05, length is 1. So 1 by 0.05. So how many divisions I will get?
800, sir.
Why 800? So then no, I am asking x direction. So x direction 1 by
Sir,
0.2.
next 20.
20, sir. 20,
Okay,
sir. X.
20 divisions. So, but how many points you will get? 21 points you will get, isn't it? If divisions are 2, 1 division,
Yes, sir.
2 points, 2 divisions, 3 points, like that.
Yes, sir.
21 points. And similarly, dy is 0.05, but it is two length.
41,
So
41
41. Okay,
points.
21 by 41 points I will get. And beta is dx by dy. And nx, that is the number of points, length by dx plus 1, and y, like height by dy plus 1. And so I am initializing the values. So everywhere this T is the temperature, Tn is new temperature, that is updated temperature, because I have to get the error. So I am taking like this. So initially I am giving 0 everywhere, but only one value I have to give 100. Okay. So T is equal to 1 to nx, that is one horizontal line, and y, that is the top line I am giving as 100. Okay, all the three I am giving is 0, and the top line boundary is given as 100. Okay, now when I go to the schemes, okay, case 1, that is point Gauss seidel. So it is taking coefficient is equal to 1 by 2 into 1 plus beta square. And so I equal to 1, 2 to nx minus 1, and j equal to 2 to n by minus 1, because it has to calculate the interior points are 1 is on the boundary and nx is on the boundary. So 2 to nx minus 1 are the interior points in which I have to calculate. In the same way, 2 to n by minus 1 in the y direction. So these are the for loops I will give. And only one equation, this is the equation, that is for point Gauss seidel. Tij k plus 1 is equal to 2 by 1 by 2 into 1 plus beta square, ti plus 1j plus ti minus 1j plus beta square into tij plus 1 plus tij minus 1. If you remember the equation, that is the way. And you can see that I minus 1j, I am taking new value. Similarly, ij minus 1 also I am taking new value, tn. The other values will be old values because it is Gauss seidel. As and when the I minus 1j, ij minus 1 are already calculated, so I take new values. Only this is the loop. It completes all the interior values, it will calculate. Similarly, I have written case 2 for point successive or relaxation. So with omega, I have written this equation. Okay, and case 3, it is line Gauss seidel. So line Gauss seidel, as I was telling, so here, how many values it will take this as array. This is one array. This is one array. This is one array. Okay, 3 arrays, and right hand values, there is one array. So 4 arrays of size n only. Okay, so some 4n values if I store, I can do the calculations. So, and I know that if you write that okay, minus. Okay, like this I have written. So the coefficient here is minus 1, this is minus 1, this is 2 into 1 plus beta square. So all these are minus 1s only. All upper triangle diagonal minus 1 only. Only diagonal elements will be 2 into 1 plus beta square. And the right hand side, so these things I have to calculate. Okay, so this is the way I get all the values. These will be given to tridag algorithm. So I have written a function because standard functions will be available. So in MATLAB also you can solve a tridiagonal matrix. Only thing is you have to give these inputs. A array, B array, C array are diagonal matrix, upper diagonal, lower diagonal, and the right hand side. These 4 arrays are to be given as the input, and it will give the output as the result. Okay, so that is the way it will be given. So I have to call that particular function. So you can see here. Yeah, this is one. It is called tridiagonal CABR. Okay, the CAB are the 3 diagonals, and R is the right hand side. So you can see that BC, this is lower triangular and this is upper triangular. 1 is given. So instead of minus 1, I am taking 1. That is multiply the equation by minus. So you'll get 1 and minus 2 into 1 plus beta square. That is minus coefficient. Okay, and right hand side beta square into Tij plus 1 plus Tij minus 1. So this is the way these 4 arrays are given to this tridiagonal function. So it will calculate new values. So that is the way. So all the methods I have written here. Okay, so if I want to, and here I given a plotting command. This is contour. Okay, so contour values. If you give all the temperature values to it, it will draw the isotherms. Okay, and here we are calculating the error. Error is equal to absolute mod Tn minus T. Okay, new values minus old values. And so it will be a matrix. At every point, it will calculate the error. And then total error is sum error all. That is, it adds all the elements of the matrix and it will give you the total error as the sum of all the elements. And this total error is checked with epsilon. Epsilon is given 0.0001, right? So with that, it will check. If it is not right, okay, if it is not, that is error is more, then this new values Tn. So this Tn will be kept in T. New values are will kept in old values, and then it will repeat. So this is the iteration for iterations 1 to n. So it will repeat that iteration. So that is the way it will continue. Is it clear everything what I am telling? Because it's very, very simple thing. You can be able to write your own code in a simple way. Okay, here I am executing it. So I am running the program. So it will asking, right? It is asking available choices 1, 2, 3, 4, 5, 6, and exit for any other number, and enter the choice of the scheme. I am giving 1. That is point Gauss seidel. Enter. And it is asking relaxation factor because it is point Gauss seidel. It is only 1 relaxation, no relaxation. So you can see this is the solution. Because I am giving 100 here, all others are zeros. If I change the values, I will get different things. Okay, you can see how many iterations it has taken. It has taken 891 iterations. Okay, I will continue. I will take second one, 2. So it is it is point successive or relaxation scheme, and enter the value of the relaxation factor. Now I can change the relaxation factor. So I will give you some 1.3. Enter. So I got the convergence and the same solution I got. But how many iterations I got here? 503. Okay. So you can see how much number of iterations it is reduced. 503 only. And so I can continue like that. So if I give 2, and so I can increase the relaxation factor 1.5. Enter. And so the number of iterations 320. Okay, 320. So again, this we will get. Okay, so if I increase it further, scheme, and 1.7 I will get. Again converged, and it is taking 166. 166 with 1.7 as the relaxation factor. So again I continue to give you 1.9. Again it is still converged. Okay, so it is and what is the number of iterations? It is taking 185. Previously 166. Okay, now it is increased. So 1.9 is not good. Okay, so between 1.7 and 1.9, maybe you may get the minimum thing. So you can see if I give some 2, okay, second scheme, if I give relaxation factor 2, so you can see it is completely divergent. So it is coming, no solution is obtained like this. So in this way, if I go to line Gauss seidel 3, and relaxation factor 1 because no relaxation. So here I can see 477 are the number of iterations, and the solution I got. Right, this is 477. If you have point Gauss seidel, it is taking some 890 or something. Okay, so almost half. But again, here with relaxation, if I take, that is fourth scheme, LSOR. And if I take the relaxation 1.3, so like this. So here, what are the number? 116 iterations. Okay, so if I continue further, fourth scheme, instead of 1.3, I give 1.5. So see, I got 5,000. So it is not converged. It didn't converge at all. So I cannot give so much relaxation for LSOR. Okay, so that is the way. So so how much I have given? 1.5. So I should not give 1.5. Suppose I give 1.4. Fourth one, 1.4. It is also didn't converge. So 1.3. Okay, near 1.3 only is the optimum value. Okay, so if I go to 5, that is ADI scheme, and no relaxation, I give 1. It is taking 464. I think it is. So it is converged, and it has taken 464. Okay, so actually, point Gauss seeded, it has taken some 890 or something. Line Gauss seeded, it has taken some 500 odd, and it is taking 464 here now. And if I ADI with relaxation, if I take sixth scheme, and if I take 1.3 here, it is converged, and it is taking 103 iterations. So it is taking 103 means I should not give more than that. If I give suppose 1.4, what happens? Sixth scheme, 1.4. So it's not, it is getting diverged. So it's not conversing. So this is the way. Is everything clear what I am telling?
Yes, sir.
Yeah. Okay, then another thing I like to, so if I give 7, it will come out of it. Okay, so execution is over. And I will tell you there is a toolbox available. Okay, in the MATLAB. I will demonstrate that also. So this can be used for parabolic, elliptic, hyperbolic, and anything. But that is solved by finite element method. But there is a toolbox available in the MATLAB. Okay, so I will tell you how to do that. Okay, before going to that, I think I will complete this PowerPoint. Okay, so the observations did same things. I will not, because how many iterations taken for each things it is given explained here. Okay, general conclusion. Iterative methods for solutions of elliptic PDEs are preferred over direct methods. This we have discussed. Okay, so we have seen mainly round of error and the number of iterations, the space and time that takes, it will be high. And and accelerated methods clearly are superior. Accelerated methods means with over relaxation, since they drastically reduce the number of iterations and the computational time, especially if the optimum relaxation parameter is known. If you know what is the optimum relaxation parameter, it reduces the computational time very much, and the number of iterations will be reduced very much. That we have observed. It comes to only 100 iterations, right? And without relaxation, it is going to 800, 500, 400 iterations. But with relaxation, it is coming to just 100 iterations. And another important thing is a good guess on the initial data required to start the solution reduces the number of iterations. So if you give, I have given 0 everywhere. But instead of that, so if I take the average 0 plus 0 plus 0 plus 100, okay, by 4, if I take the average of all the 4 temperatures, 25 everywhere, the number of iterations can be very much reduced, even more than that. Okay, so that is another thing. And for line iterative methods, application of the finite difference equation in the direction of larger change increases the convergence rate. So wherever I told you, right? So based on which boundary is more important, if I sweep in that direction, the number of iterations can be reduced. I have to see that that information goes first into the domain so that the number of iterations can be reduced. Okay, these are the general conclusions. Okay, I will tell you how to use the toolbox. Okay, you just have to type PDE tool. Okay, so this is one I have to type. I'm getting this like this. Okay, so then what type of problem? Okay, options, then applications. So there are various applications are there: structural problems, electrostatic problems, magnetostatic problems, AC power electromagnetics problem, conductive. So whatever is the type of problem, the equations will be similar type of equations. This is second order differential equation. So similar equations will be there, either elliptic, parabolic, or hyperbolic. Okay, so you can choose one of them because ours is heat transfer things. So I take heat transfer. It comes here, right? So here heat transfer. Okay. So once I do that, I have to choose which type of equation I'm going to solve. PDE. Okay, this partial differential equation. If I click here, I'm going to get PDE mode. No, not this. I think here I type. Oh yeah, here. I don't know how to undo it. Edit. Okay, just I will go back. I don't know why it came. Okay, PDE tool. Okay, I've taken options, applications, e-transfer. Then here, if I type PDE, so what type of equation? It is elliptic, parabolic, or hyperbolic, or eigenvalue type. Okay, so I am taking elliptic equation. So in the elliptic equation, a generalized equation is given here. This is del dot k del t is equal to heat generation plus h into text minus t. Okay, so it is a general one. It is having that is convective boundary or heat flux boundary or what type of equation it is there. So based on that, a generalized equation is given. But our equation is del square t equal to 0. So del square t equal to 0 means this is del dot k del t. So k will be 1. So k is 1, it is there. And the right hand side should be 0. So capital Q should be 0. So this I will make it 0. And this h should be 0. So if I take like this, I'm going to get del square t equal to 0, which is elliptic equation or Laplace's equation. If I have a heat flux, that is like Poisson equation, that q value, you have to give something. So here, if I give q some value, yeah, it will solve heat generation equation. Okay, so this is over. And so now I have to give the boundary domain. I have to take some rectangle. So this is a rectangle. This is also rectangle. It comes from edge. It comes from the center and the ellipse, and some simple domains are there. So suppose if I take this, so it will come some rectangle like this. Okay. So I have given something, but I have to give some lengths for it, right? So I double click on this. So left boundary, bottom boundary, width, height, it is given. Okay, left boundary, I'm taking 0. And the bottom also, I take 0. And width, I have to take 1, right? 1. And height, I have to take 2. Okay, so okay. So it is obtained like this. And I can give axis limits. I think options, axis limits are there. So for x-axis, it is 0 to 1. I can give 0 to 2 if I want. 0, comma 2 on the x-axis, and here I can take some 0 to 3. 0, comma 3. So I can see the domain, whole domain like this. Okay. So this is 0 to 2, 0 to 2. This is 1 and this is 2, right? Apply. Okay, this is the domain. Okay, so on the x-axis it is 1 and the y-axis it is 2. And so actually there is something like axis equal also is there. So you can see both sides same scale it is taking. So I can see this is the domain. Okay, so the domain is chosen. Then I have to give the boundary conditions. So there is boundary or this d omega. This is boundary actually. So if I click on that, so it is ready. All the boundaries, they are ready to take. Okay. So here, if I click on this boundary, it is coming like this. So ht equal to r something. Now I have to get t equal to 0, t equal to 100 like that. I can, or if I have a Newman condition, I have to choose like this. And it is asking like this. Okay. So this is a general form of Newman condition. But if I have Dirichlet condition, it is coming like this. So here r equal to 0 and h equal to 1. Okay. So this gives t equal to 0 on the left boundary. Okay. On the right boundary also same thing. Okay, same thing 1 0. And on the bottom boundary also 1 0. Okay. On the top boundary, I give r equal to 100. Okay, boundary conditions are given. So next I have to generate the grid. So here either I have to go to mesh or this triangle. If I click on the triangle, automatically the mesh came. And if you want to refine the mesh, so again you can go to mesh and refine mesh, or you can click on this multiple triangles. So it will come like this. And there is one more option for finer grid. It is a jiggle mesh. So if I do that, so it will get a better mesh. Okay, mesh generation is over. So pre-processing is over. Now I have to process it. So I have to solve it. So I can go for solve parameters, or I can click this equal to. Okay, so this solves it. See, now I got it. So these are temperature. You can see high temperature here. This is high temperature region 100. And as I come down, the low temperatures are there. If I want contours, I can plot. So I can go to plot parameters and I can take contours and just click plot. So you can see, is it clear? So this is the way I get. So if I want, I can change the boundary conditions without changing many of the things. I can just change the boundary conditions. So suppose I take the right side also 100. Okay. So right side boundary also, if I take 100, so I go to this boundary conditions and this right boundary, I take this as 100. I'm not doing anything else. Just I will solve it. So go equal to. Now you can see this is the way, because this is 100 and this is 100. All this side is high temperatures and these two sides are low temperature. Am I clear? Could you see all of them?
Yes, sir.
And even if I want to have, I can have Newman condition on the right side. Suppose I take Newman condition, means I will take it as insulated. Insulated means heat flux equal to 0. So that is that if I want to take, again go to d omega and right click on this. Sorry, click on this. And here I go to Newman. So in the Newman, this right side, it is equal to 0. So G equal to 0. This is okay, Newman only. And Q is 0. So this is 0. So I will get del T equal to 0. Means gradient of T equal to 0. This is Newman condition. So if I say okay, so what is the way I'm going to get? So on this boundary, I am taking slope of the line equal to 0. That is, slope of the temperature line or isotherm is equal to 0. So what type of lines I have to get? I have to get horizontal lines near that boundary. Am I right? Because slope is 0, dt equal to 0. So you can see that equal to, if I click, you can see here. Is it clear? So you can
Yes,
see
sir.
we can play with it, right? Just change the boundary conditions, change the geometry, change the equation, anything you can do. And this can be easily used for elliptic, parabolic, hyperbolic, anything. So all these things, the equations can be solved. Okay, so this one also I wanted to demonstrate. So you can just play with it. You can use it and play with it. And so you should be able to write a code or use the toolbox for simple equations, simple model equations like elliptic, parabolic, hyperbolic. In elliptic, del square of something like Laplace's equation or Poisson equation, you should be able to solve. Any questions? So next class we will start parabolic equations. So parabolic
Sir,
equation.
please do share that MATLAB code also, sir. We will see that.
Okay, okay. Okay, I will send the code to you. Okay, the source code I will
Okay,
send.
thank you, sir.
Okay. And actually, if you try it, it is better. There is nothing much.
Yes, sir. We will try only. Yes, sir.
Yeah,
We will try only, but we get some stuck
yeah,
at
yeah.
some point, so it will help us.
Yeah, it will guide you, right? Anyhow, so it will give you some guidance how to uh, treat
Yes,
your
sir.
logic, right? So if you, I will send this code, but when I do the parabolic and hyperbolic, you can try first initially how to do that, because once you understand the logic, it's not a big thing. Because I think
Yes,
MATLAB,
sir.
only people who have taken the training, I think the workshop or attended the workshop, they will know. Other people may not know, right? Anybody attended the workshop, MATLAB workshop during your tenure? Is it conducted?
Mm.
Yes,
Only
sir, it was.
Mechanical Association once conducted, sir.
Mechanical Engineering Association, Harikumar sir normally conducts. Have you
Yes, sir.
anybody? Have any of you attended?
Like I have attended the session, but not completely, sir. In
Yeah.
second year once.
Yeah, once, see, normally all these it is like language only. In my childhood, I know because I have a community where all other language people, each house, there used to be different language person. Like Punjabis are there, Marwadis are there, Oriya people are there, and all like that. And in my childhood, it seems I used to speak their own language whenever I go to their home. I used to know all the languages. Now I don't remember anything. In my IASC Bangalore, I got certificate for German, Russian, and French. Three certificates I got. I have attended the courses, and I was uh, maintaining the first there. But now I don't know even how to wish it also. So these are like languages, even computer languages also. If you don't use them, right, you will forget. Only thing usage only that is more important. Okay. Anyhow, that's so. Next class we will go for parabolic solvers. Shall we go for the story?
Yes, sir.
Yes, sir.
Yeah. I don't know whether I have told this story for. Okay. So it's a beautiful heart story. I liked it very much. I will say that. So a young man was proud of his healthy and beautiful heart. One day, standing in the middle of the town, he proclaimed that he had the most beautiful heart in the whole valley. So a large crowd gathered to have a look at his heart. His heart was smooth, shiny, and looked very healthy. Indeed, the man had the most beautiful heart in the valley. Everyone agreed. The proud young man felt delighted and boasted his perfect heart, which everyone admired. Suddenly, a voice from the crowd said, "Your heart is not as beautiful as mine." The young man searched for the person behind the voice, and an old man appeared in front of him. And show us your heart if you have if you believe. Sorry. So if you believe you have more beautiful heart than mine, said the young man. And the old man carefully showed his heart. The crowd and the young man looked at the old man's heart, and the heart was beating strongly and healthily, but it was not smooth and shiny as the young man's heart. Instead, it had scars and uh, all scars all over it. It had places where some pieces of the heart had been removed and other pieces were put in, and the other pieces didn't fit perfectly, and there were several uneven edges. So, in some places, there were deep gouges where some pieces were missing. And the crowd laughed at the old man's heart. How can you claim that he has the most beautiful heart when it is all scarred and uneven? They thought. And the young man looked at the old man's heart and laughed. You must be kidding. Compare your heart and mine. My heart looks perfect and smooth, and yours is a mess of scars and tears. Yes, your heart looks perfect, but I would never trade your heart with mine, said the old man. Every scar in my heart represents a person whom I have given my love. I tear a piece of my heart and give it to them. Often, my loved ones gives me back a piece of their heart, which fits into the empty place in my heart. Since everyone loves each other in a different way, their piece of heart may not perfectly fit my heart, so you can see some rough edges. These scars and rough edges remind me of the love we shared, he continued. Sometimes I would give a piece of my heart, but the other person may not return a piece of his heart to me. These are the empty gouges. Although these gouges are painful, these remind me of the love I have for these people too. So, do you now see what a true beauty is? Asked the old man. The young man and the crowd stood silently with tears running down their cheeks. The young man walked to the old man, reached into his perfect young and beautiful heart, and ripped a piece out of it and offered it to the man with trembling hands. The old man gratefully received his offering, placed it in his heart, and then took a piece from his whole old heart and placed it in the young man's heart. The young man looked at his heart. It did not look shiny and smooth like it used to be, but it was now more beautiful because he could feel the love from the old man's heart flowing into him. They embraced and walked away side by side. Love is but the discovery of ourselves in others and the delight in the recognition. Thank you very much. Thank you.
Sir, you have to cross that.
Yeah, yeah.
Thank you.
Thank you.
Sir, will you share the assignment?